Welcome to note set number 30, where we'll talk about yet another, a second way of doing linear phase FIR design, leading up to the real powerhouse method that we'll talk about in subsequent note set. So this approach is called the frequency sampling method, and it's covered in section 10.2.3 of Proachus and Monolachus. Okay, so here's the basic idea. So suppose you've got a desired frequency response, just like we've been saying, and we'll call that H sub D, and we can't necessarily achieve that exactly with a realizable causal filter. So we've got that, and we can come back to some corresponding impulse response. And you'll note that I've changed from our standard minus pi to pi to integrating from 0 to 2 pi. That doesn't really have any effect at all, because I can integrate over any interval of length 2 pi, and I get exactly the same thing because of the periodic nature of this and the periodic nature of that. So when we do that, whatever we get for this will not necessarily be an FIR filter. So we need to take some steps, as we've seen in the previous set of notes, to try to force that to be an FIR filter. In the previous set of notes, we created that, and then we shifted it out far enough and truncated both at the beginning and end, symmetrically around the center of it, so that we ended up with a nice FIR filter that had symmetry and gave us the linear phase. What we're going to do here is say, well, you know what? When I do this DTFT, I may get infinitely many points here. But if I think about doing an inverse DFT as a stand-in, and I, instead of taking infinitely many points here, I take a finite number of points from this, apply an IDFT, then I'll get a finite duration signal in the time domain. So maybe that will work. We use the IDFT on frequency samples of this. So we'll define just taking samples every 2 pi over capital M. We'll do this way at first, and then we'll, since this is the basic idea, and then we'll expand on this idea a little bit. So we just take equally spaced points, and you can see why I changed this to go from 0 to 2 pi up here, because the explicit definition of the DFT goes over that range. So that allows us to go k 0 out to m minus 1, and that covers the 0 to 2 pi range. So if we take those samples, here's our h of k, which we've selected out as samples of that, and we just do an inverse DFT, we're going to get an h of n that will be finite in duration and should be related to somewhat to the shape of this thing. And so that's the basic idea. And then we can find out what our design actually ended up looking like by then transforming back into the frequency domain, but using a real DTFT to do that. And here I'm saying let's look at it from minus pi to pi to see what it really looks like. So this last step is not part of the design, it's just part of the check to see how things actually turned out. Okay, going to the next slide here. This is just a nice picture of what we're doing, and I borrowed this from yet another book, this one by someone named Lathy, a book with the title of Signal Processing in Linear Systems. Really more of a signals and systems book, but goes into a lot of detail on a lot of this discrete time stuff that we're studying here. So the idea is we start with this rectangular ideal filter here that looks like this and continues out like this. It's a little hard to see it. Well, that's because he kind of draws it on both sides. And so that's our desired filter, and as the ideal frequency response. And we then take points from 0 out to, well, we're showing 0 out to pi here. Yeah, I'm not really sure. I think I relabeled this, and this really should be 0 out to 2 pi. So I don't think I got this quite right. So all of these I think should be multiplied by 2 to get this right, because here's the pi point. So we take our points. 1 here, then 0, 0. So forget about the wiggling curve here. We're really looking at the points on the ideal curve there. So those are the points that would go into our DFT, actually our inverse DFT. You take the inverse DFT of that, you get an h of n, then you compute the dTFT of that, and you end up getting this curve. And so that's the curve of the actual designed filter. Now, again, we're using like 8 points here, so this is not a very good design. And when we look at it flopping back over to the real negative frequencies, we would get something that looks like that. So, so this is just an illustration of the idea, not the capabilities of this, because we have we're only using 8 points here. Okay, so and obviously increasing the number of points that we would use will improve the design. Okay, so and we've not really done anything here to account for the linear phase. So all we've done here is just try to match the magnitude response of this. So to account for the linear phase before we do the inverse DFT, we would have our specified magnitude values. And then, based upon the number m that we have, we would include this linear phase term. So we would have our magnitude values out in front. We'd have our linear phase term, and then this comes from the machinery of the DFT. And so that would ensure that we would get the appropriate linear phase out of this. So let's expand this idea. We've seen that windows are helpful, and one of the things here is that we just said that we would really like to be able to nail down a finer grid in the frequency domain, because we see that the result kind of wiggles between those values, so it gets nailed down to equal to those values on the grid, but then kind of puffs up or down in between those. So if we can use a finer grid, we would get less of that quote-unquote puffing up and down. But unfortunately, to use a finer grid would mean we would have to use a longer filter length. So we try to get both of best world, both of those, the best of both worlds. That's what I'm trying to say. We use a finer frequency sampling grid. And so we end up specifying the frequency response at a much higher, at a much finer grid, but we get a much larger number of samples. So unfortunately, when we do that, the n value will be much, much greater than our desired FIR filter length. So we're specifying this at a much finer grid, with many more points. Then we do our linear phase, but we do our linear phase according to the desired length that we want to end up with. Do the inverse DFT with n being the size of our DFT, and that gives us an h tilde of n, which is very long, but then the final thing that we do is we truncate to length m, and we apply some non-rectangular window to that. So that non-rectangular window simultaneously truncates it and reshapes it. And so that's the basic idea of this approach. And so MATLAB has a command that does this, and I will tell you that the book's coverage of this is quite a bit different than this, and a much more generic and general way of doing this. So I'm not sure you really need to read through this section. I think what I talked about here is pretty sufficient and enough explanation. And MATLAB has a command called FIR2. So we had FIR1 for the windowed method. We have FIR2 for the frequency sampling method. So what do we need to specify here? Well, we need to specify n, which is the order, not the length. We need to specify f and a. So the vectors f and a tell us the values that we're looking for, but not all the points. It's just kind of laying out, it's this value over this region, and then it's this value over this region. So the vectors f and a specify frequency and magnitude breakpoints. So we're down here we're saying 0 to 0.6 and 0.6 to 1. That's defining two different regions. So 0 to 0.6 would be our pass band, and 0.6 to 1 would be our stop band. And you can see that we're saying from 0 to 0.6, we're specifying the magnitude to be 1 during that over that interval, and then from 0.6 up to 1, we're saying it should be 0. And what the MATLAB command does is, based upon that and based upon the numbers that you're specifying, so we're specifying the order of the filter, it then goes to a default parameter called NPT. Basically, it puts whatever that is, 512 points between 0 and pi. So effectively, it uses n times NPT frequency points over the whole 0 to 2 pi range. So it just uses these to then get 512 equally spaced points between 0 and 1, or the equivalent 0 and pi. So then it does the inverse DFT back into the time domain and applies an appropriate window. So there is a way to specify the window. The default window is the Hamming, and if you want more details on how this all works, you can ask for help within MATLAB, but it's pretty straightforward to design this, to call this, at least using the default characteristics. So I'm not going to go into a lot more detail on this. Again, this is kind of not the main way of designing FIR filters anymore, but it was at one time put forward as a usable FIR filter design, and you should be aware of it because sometimes you run across it. Okay, last for this set of notes, just comparing FIR1 versus FIR2. Basically, MATLAB is giving you some guidance saying that you can use FIR2 for standard low pass, band pass, high pass, band stop, multi-band, and what it's not good at is coming up with some arbitrary frequency response. You want it to do something interesting or different in some band, that would be a good time to use FIR2. Although we'll see that the kind of premier method that we'll talk about next can also be used for these kind of arbitrary frequency responses. And I've given you some links here that give lots of details on how to use each of these two commands. So you can go check those things out. So that's it for frequency sample design using FIR2 command in MATLAB. And the method that we'll talk about next is called the Parks-McClellan equiripple design, also called the Remez exchange-based design. And it really is the premier method for designing FIR filters. So we'll see you next time.